Hello everyone and welcome back to another video. Today we are doing molecular orbitals with Diels Alder. So to start, what is Diels Alder? Basically, it's an overlap between specific molecular orbitals. So the specific molecular orbitals we'll cover very soon. So at least one conjugated system is necessary. We'll also go over what conjugation means in a moment. But essentially what you have is you have these orbitals on this carbon 4 and this carbon 1 overlap with the orbitals of carbon 5 and carbon 6 respectively. Right, as you can see, these orbitals match. Got the white with the white and the black with the black, right? So the matching of these orbitals is extremely important, and this configuration cannot be understated. All right, so what is conjugation? Conjugation is when three or more atoms participate in a pi system. This can occur through either direct double bond proximity or just simply resonance, right? So here's some examples of conjugated and not conjugated systems. Well, I'm going to start with the not conjugated first, just to show what it means to not really be conjugated, right? So here you have a double bond, right? So you have two atoms that are part of a pi system. So this carbon atom and this carbon atom, right? Since there is no third carbon atom that's part of the pi system, right? It is not conjugated. And the same applies for the other two examples of non-conjugated part of the screen. So what does it mean to really be conjugated? Three or more atoms are participating in a pi system. Or you just have adjacent double bonds, right? But I don't really like the definition of adjacent double bonds because it doesn't tell you the whole picture, and also you have to remember resonance, right? So let's start with this one up here. So the double bonds here are not adjacent, but we can make them adjacent, right? We can propel the electrons here, right, into this double bond, and we can, through resonance, just transfer these electrons into this atom, right? So we would get a structure, a resonance structure, right, like that, right? So you are conjugated. This molecule is conjugated in this essence, right? Pardon that. So what about this benzene ring? Well, it is conjugated. It's actually conjugated all the way around, and it is aromatic, but we will be going over that in a different video, right? What about this ring right here? Well, since this carbon, and this carbon are part of a pi system, also this carbon, right? It is conjugated. Even if one of these double bonds down here, and as in, even if this double bond did not exist, it would still be conjugated. Just because three atoms are participating in the pi system. Same goes for this molecule down here. You have 1, 2, 3, 1, 2, 3. So actually there's multiple pairs of double bonds here that are conjugated, which is great for stability. And this last molecule down here. Now similar to this first molecule over here, right? This last molecule through resonance, right? We can push, so we know we have a plus charge on this bond, so we can push this double bond over and we'll make it conjugated. Hopefully that makes sense to everyone. All right, moving on. So right back to Diels Alder and molecular orbitals. Why do we bother explaining to you what conjugated even means? Well, in Diels Alder, you always have a conjugated diene. So diene means two double bonds, like diene, like alkene, right? Two double bonds, and a dienophile. Dienophile just has one double bond. Diene always has two, right? And similar to the second slide, actually, this is actually how the overlap would occur in line structure format, right? So you have your diene, and you have your dienophile, and that makes us a lovely ring. So usually in Diels Alder, you are always making a six-membered ring as a product of the reaction. The second rule for Diels Alder. So the diene has to be conjugated and in the cis position due to orbital geometry, right? So this would work, right? Because we do have a conjugation, check, right? So it's conjugated, right? So check. Is it in the cis position? Yes, it is. Is this in the cis position and conjugated? Yes, right? What would not work is something like this. So this is not conjugated, not conjugated, and because of that, right, it would not work. It's also not in the cis position, right? But obviously that's because it's not conjugated. This, even though this is conjugated, right, it's not in the cis position, right? So because of that, right, there's no way for this Diels Alder reaction to take place because this molecule cannot twist to into itself into this type of position. It's simply locked, and thus it would not work in Diels Alder. All right, rule number 3, right? So the HOMO of the diene, right, reacts with the LUMO of the dienophile. So if you remember what HOMO and LUMO are, so HOMO means the highest occupied molecular orbital, right? And the LUMO, lowest unoccupied molecular orbital, right? And they have to be in phase. So this in phase component is extremely important. If you remember from the second slide, right, where we talked about the phases, right? Essentially, colors need to match with colors. That's like an oversimplification. But what we're looking at is, so if you can see, this reaction is the same reaction as on slide 4. So this slide, all right, where we have your diene and dienophile. You have 2, 3, or so 1, 3 butadiene, right? And you have ethene, and they react together to make this ring. So in this case, we're doing the same reaction here, but I'm drawing out the orbitals for you, right? So we have our 1,3 butadiene, right? And we have our ethene. So first we start with 0 nodes. We know that all these nodes, if you remember from our first video, right, all of these nodes are in phase because all these orbitals are in phase. They're all the same. Then you have this node down here, and then you have 2 nodes, 1 and 2, right? So because of this third rule, right, the HOMO must react with the LUMO, right? All we really care about is this drawing right here, this particular orbital schematic, right? And all we care about is this one right here. So the rest don't really matter at this moment, right? Let's go over how these connect. The nodes that we care about are the outer nodes of the structure of butadiene, right? So we care about right here and right here. And sorry, by nodes I mean pi orbitals, right? The pi orbitals that we care about. So the pi orbitals that we care about are these outer pi orbitals over here. And I mean, here we care about both of them. So they need to be in phase, right, with this structure. And as you can see, right, if I were to redraw this structure, this 3-butadiene, right, I'm just going to draw the outer part of the nodes, of the orbitals. So I keep saying nodes, orbitals. And like so, right? All we care about is these ends right here. And these are the orbitals of our, let me draw that better, right? Our dienophile. So we just care about this sort of overlap right here. And so in this case, this reaction would actually occur because you do get this overlap, right? So black pairs with black and white pairs with white in this case, and the reaction would occur. So that is essentially how Diels Alder would work just based through molecular orbitals. So let's go talk about the inverse demand part of Diels Alder. So yes, we said that the HOMO of the diene must react with the LUMO of the dienophile, but it could go backwards as well. The LUMO of the diene could react with the HOMO of the dienophile. It is just less energetically favorable, right? They also need to be in phase, so nothing changes. They still need to be in phase, right? So the only trick about this right here, as you can see, so these guys need to match up with these. So one important thing with the is that you hopefully you by now understand that this configuration is identical to this configuration. All we did was, I mean, it's the same thing. Well, you can either rotate the molecule, right, or you can think of it as just starting like just determining coloration. It really doesn't matter, right? But in this case, right, it would react as you can see because you have black down here, right? And you have black up here. and so you would get the reaction. But just it's important to know that with Diels Alder and molecular orbitals, it would occur uh, in an inverse demand situation. It's just unlikely to happen because it's less energetically favorable. All right. So let's do a first practice question. So pause, try it on your own. All right, welcome back. Um, let's start. So this reaction, right, might be a little scary, but that's okay, right? This video, the whole point of this video is not to learn Diels Alder or conjugation in depth. I just want you to get the surface definition. I really want you to know how to apply the molecular orbital theory that we did in the first video to these types of problems, right? So really, all we're doing is drawing the orbitals that react in the following reaction. So what's the very first thing that we do? Well, we have to draw the orbital diagram, right? We have to draw the nodes. So let's start with this on the right, this structure on the left, right? So the first thing I need to do, right, is I need to draw out just the frame. So since these are sp3 carbons, right here and right here, they really don't partake in the pi system, right? Because all we care about is these carbons down here, right? 1, 2, 3, and 4. So because of that, we can just ignore it in our schematic. We don't really need to draw it, right? So we're going to start with 0 nodes, right? So 0 nodes, right? So 0 nodes, they're all going to be in the same configuration. So let's just say dark is on the bottom, and that's 0 nodes, right? Okay. And then 1 nodes, right? That's 1 nodes, right? So remember we have 1 going down the middle, right? So we're gonna let's keep this side the same, and let's change the side. Boom. All right. And remember, we have to denote the amount of electrons that we have. So here we have a total of 4 pi electrons, right? 2 from this double bond and 2 from this double bond. Okay? So this is the HOMO of the diene, right? So we can stop right here. No need to draw any more phases or nodes, right? We're good, right? So this is it for this left diagram, right? On the right side, right, it is dienophile. Once again, right, dienophile, remember, you don't need to have a conjugated system for a dienophile. You could, right, in some scenarios you could, but you don't need to have one. All you need is just one double bond, right? So we can kind of ignore this carbon right here, right? We'll still draw it, but it doesn't really matter that it's there. It doesn't really affect our answer. So let's draw like so. And I'm going to start from this side to identify the LUMO. So we only have 2 electrons, right? That's it. So this is going to be our LUMO, the second drawing. So we're going to start from the bottom, right? We only have 2 orbitals that are in play here. I'm going to color the bottom dark just to keep it the same. And remember, the first node will always be down the middle. And you get that. All right? So there's our HOMO, and there's our LUMO. So that's it. That's our answer, right? So you have that, and you have that. Now, you might be wondering, well, what if I decided to draw the bottom part of the orbital white instead of black? That's completely fine, right? Another acceptable answer would be just inverting everything that I drew. So basically, I'm just going to swap everything, and that is another answer. So if you're doing like a question, right, and you see, oh, for some reason my answer does not match up, well, consider the other type of phase overlap that could happen, right? And there you go. Hopefully that makes sense to everyone, right? And that's the first practice question. So let's move on to the second practice question. So this is a pseudo Diels Alder reaction, right? It's not exactly Diels Alder, but it, it, it works along the same way. So we're gonna pretend, right, that it is, right? And so we're gonna do the exact same thing that we did for the first practice question. So pause it, try it on your own, come back. Welcome back, right? So let's start by drawing in a similar fashion, right? We're gonna draw this on the left side. We're gonna start with the dienophile, right? Even though we don't have two double bonds, like I said, pseudo Diels Alder, so we're gonna go exactly the way that we approached it originally, right? So we have 4 electrons to work with, right? Don't forget about these two right here, right? And I'm gonna start by drawing my orbitals, right? So here, they're all 0 nodes, so they're all in phase. And here, since the center node, the node to be symmetrical, it has to be in the center. We're not going to draw that orbital. If you're confused as to why we don't do that, please refer to our original video, right? And boom. So that is our HOMO, right? And then same exact thing that we did in the previous video for our LUMO. So hopefully you are understanding how to do these problems because their structure is going to be very similar. Just because Diels Alder, right? Dienophile every time. You're always going to have something like that. Oh, sorry. I'm going to color this one dark and this. And I knew this was going to be the Lumo just because of this, just how we drew this file. Okay, so hopefully that makes sense. So this is going to be your final answer right here. You're gonna have this is your HOMO and this is your LUMO. And I understand, right? There's also another acceptable answer if you just invert these phases, right? You're gonna get dark on top, dark on the bottom. That's also correct, right? And if you do here, you're gonna get dark on top, dark on the bottom, right? Both are correct. Okay. All right. Thank you for watching. Hopefully that answered any questions that you had related to molecular orbitals with Diels Alder. So this is a relatively short topic because there's really not much you can test here. I mean, it's just the same thing as we did originally, right, with orbital theory. So in the next few videos, we're going to be covering Diels Alder and everything that has to do with its conjugation, right, Diels Alder, and then we'll segue into some cool retro and intramolecular Diels Alder videos as well. Great. Thank you so much for watching and I hope to catch you next time. Bye bye.